All right, so the next item on our list is, okay, that's all nice. I got, how much current's flowing through a wire, and that's kind of fun, but I don't as yet know why I want to know that. In other words, how do I turn what's happening inside of a circuit to what's outside of a circuit? How much energy or whatever else? The answer is we're going to use power to get in and out. Now, as a reminder, we talked about voltage. Voltage is a desire per unit charge, how much energy per unit charge. It literally is that. A volt is equal to a joule per coulomb, right? So as such, right, it's our energy per every coulomb. So backing up a little bit, if I take a 9-volt battery and I let 4 coulombs come from one side of the 9-volt battery to the other side of the 9-volt battery. Picture a 9-volt battery. I got a wire here, and I run it through a heater. Cruddy wire, cruddy wire, cruddy wire, cruddy wire. Call the resistor. Comes back here. If I let 4 coulombs run to the other side of the battery, they go out here, go running through this thing, go out the other side, I'll have made 36 joules of heat. Okay, that's pretty straightforward, right? If you know your voltage of battery, you know how much charge comes out of your battery, that's great. The problem is, we really don't regulate by charge. Instead, we're going to regulate using power. Okay, so if VQ is equal to energy, again, oddly enough, you don't need to know this formula, which really drives me crazy. AP Central should actually have this as part of their formula sheet. But I find if I go down this road, we go a long ways down this road, there's really no reason to do that. So I'm just going to briefly mention it, and then later on we can talk about it more. And then we know, so this would be energy over here. You guys don't know what U is. So energy. So power equals energy divided by time. And so that's going to be VQ over T or VI. And actually they use IV. So here's the formula you'd find on your formula sheet. Don't use this ever. Now, I'm going to give you a really simple worksheet. It's going to work on the worksheet everywhere. And so if you want to ignore me and just use P equals IV and happily live your life smiling about how smart you are and how wonderful the universe is, you will be a genius. Unfortunately, when we get later in the chapter, you'll start getting all sorts of problems wrong. You won't have the foggiest idea why. Actually, I'll explain it to you, and then you'll be even more angry. So what we're going to do is we're going to switch the V for what V is equal. V is equal to IR, right? So we're going to go P equals I times IR. And the formula Mr. Resney says you should use is P equals I squared R. This is the formula I want you to use. Now, sometimes this means you're doing a lot more work to get your answer. I apologize for that. But this gets you the right answer every time, even when something sneaky is going on, right? So therefore, I want you to get used to using this, and this is the formula I want you to use. I will also tell you this. Oftentimes, AP Central assumes you know this formula, and you don't know this formula, and so they do something really tricky, which makes this one really easy to use and this one really hard to use. So you're much better off using this to begin with. Everywhere but the first worksheet I gave you. First worksheet I gave you, if you use this, there's nothing I can do to stop you. I'm not going to be able to stop you. Which brings up a point. I have 2 example problems. Oh, by the way, what's power measured in? I said watts. Yeah, watts. Okay. And then this is current, which is amps, and this is resistance, which is ohms, right? All right, so I have 2 example problems. Number 1 and 2 are waiting for you. Have at. Try those 2 example problems, and then we'll talk about how to draw a circuit. That sounds more exciting than it is. We'll get there in just a second. So 3, 2, 1, do those problems and pause. All right, so let's talk about how you do example problem number 1. Example problem number 1. The current to a 60-watt light bulb is 2 amps. What's the resistance of the light bulb? Huh. All right. Power equals I squared R. No, we're not using that other formula. 60 equals 2 squared times R. R equals 15 ohms. Isn't that nice? Yes, that's an ohms. Look how bad that is. Whatever. Okay. Then the next question is a 12-volt battery. A 12-volt battery causes a flow of 2 amps through a lamp. What is the power of that lamp? So I'm going to go P equals I squared R. P equals 2 squared times, oh, I don't know the resistance. So now I'm going to have to use my second equation, which is I squared R. 12 equals, no, B equals IR, my bad. You with me so far? Oh, backwards. So B equals IR, that was a wrong formula. So I equals 2, R equals I don't know. Solve for R, I get R equals 6 ohms. Now that I have 6 ohms, I can go back here, throw the 6 ohms right here. I get power equals 2 squared times 6, which is 24 watts. That's what it is. It's in watts, all right? All right, so now the next question is, how do you draw a circuit so that you and me can agree what's there? And so there are symbols for the various items you're going to find in a circuit. The first symbol is called a resistor. Okay, resistors look like this. Boop. Why are they? Because they're cruddy wires, like literally cruddy wires. So I should draw that better. It's just straight zigzags. That's a resistor. Okay, voltage source. Okay, in this class, a voltage source. Oh, wow. Okay, it's even worse than normal. Voltage source is actually a battery. Now, a battery has plates inside of it, right? Those little metal strips inside of it. And so we use big strips and little strips to represent a positive side of the battery and a negative side of the battery. But here's something interesting. Your 6-volt battery has 4 cells in it. So we, being crazy, we like to write 4 cells. Okay, so we have 4 sets of strips to take care of each one of those 1.5. You wonder why batteries are 1.5, then 6 and 9 and 15. Why aren't they something in between? Because each cell is worth 1.5 volts, and so if you have 4 of them together, you have a 6-volt battery. You have 6 of them together, you have a 9-volt battery. If you have one of them, even if it's a big one, it's still 1.5 volts. Now, I'm going to tell you the truth. We're never going to care about how many cells there are. Draw as many as you want. Okay, probably good to draw 2 because there's something similar to this type of diagram which you don't want to make confused. Okay, something called a capacitor, which we're not going to talk about this year, but is 2 equal length posts like this, right? And so if you draw your battery like this, even if you draw your lines pretty close to the same length, if you got 2 cells, nobody's going to confuse that for a capacitor. Okay, all right. So this is a battery. Also a reminder, the big post is the positive side, little post is the negative side. Almost never matters. In fact, most problems, they're going to say put one in. They're going to tell you which side is attached to which because it doesn't matter. Who cares? Okay. All right. How do you draw a wire? That's a non-cruddy wire, so that's our wire. It's a straight line. Okay. Cross, no connection. There's a couple ways to do this. The way we're going to do it in this class is we're going to go, I've got a wire here. This wire is going to cross it, but it's not going to hit it, so it's going to hop over it. Oh, yeah, it's hopping over it, okay? Which means it's not connected, okay? That's telling me not connected. If I do this, that means they're connected, okay? Connected. Sometimes AP Central likes to draw a little circle in the middle there, just for the record, just in case you see it. Don't panic, that means they're connected still. Okay, the next one is fuse. Fuse. How do I draw a fuse? Okay, well, first of all, what the heck is a fuse? Okay, so if you look on the back of 9.3, look on the back of 9.3, if I can find my back of 9.3, it says what are fuses. Let's talk about that now. What a fuse is if you look at a fuse closely from your car or wherever else, you hopefully don't have one in your house anymore. Those you used to put in the houses all the time. It has a metal cap, and then these attached to a normal copper wire, right? There's a little skinny wire in the middle. So what does this thing do? It breaks. Mr. Resney, why would I want a fuse to break? What is wrong with you? That is not a good thing to have a wire break. Well, yeah, it is sometimes. So first of all, this little tiny metal wire creates some resistance, right? Because it's tiny and smaller. So electricity flowing in here is going to feel the resistance here, and it's going to create some I squared R. Because it's very thin, if the current gets above a certain number, it gets very hot very fast, and this thing will melt. When it melts, it breaks the circuit because the electrons can't get through here anymore. Okay, so you have a set of these in your car. Why do you have them in your car? I'll tell you why you have them in your car. Example I will give you is I once drove out to Arizona on a backpacking trip. When I got back, as I was driving back, I stopped at a place and my fuse had blown. Well, what that meant was I couldn't start my car. Well, I'm in the middle of the desert. I'm going to die if I don't fix this. So I took a copper penny and I put it right in the same little slot, attached to bits of metal, and my car started right up and it wasn't a problem. But in the back of your mind, something should be bothering me. What? Why did the fuse blow? Well, because it's got too much electricity going through it. Okay? This is to protect me from too much electricity going through the wire. But that's okay. I'm not worried about it because I was in college and I had bigger things to do. So I driven another 200 miles. This was completely unrelated, by the way. When I pulled into a gas station, filled up my tank, pushed down the gas pedal, and the gas cable broke. Huh, that's a bummer. So my starter had broken. Now my gas cable had broken. So I went into the local hardware store, my local automotive store. I said, hey, look, I need an acceleration cable for my Dodge pickup truck, to which they said, we don't have one. And I scratched my head and said, well, Volkswagen Bugs have their engine in the back. And the gas pedal's up here. So clearly their cable for making the thing go, their accelerator cable's got to be longer than my acceleration cable. So I went and bought one from the store. I bought a Volkswagen cable. And then I went and put it in next to my pedal, ran it through the car, ran it up to the top of the carburetor, and I had about 5 feet extra. You can't just leave that laying around, so I made a really big bow. Isn't that nice? Made a really big bow. All right. So now you'd think you'd go and get that fixed at the automotive store at the moment you get there. I mean, acceleration cables cost you nothing. So do fuses, by the way. But I'm not worried about it. 6 months later, I pull up in front of my friend's house. And I open up the car door, and I go walking towards his front. He opens up the door to say hi to me, and he immediately gets a look on his face like I'm going to attack him or something awful's happening behind me. So I turn around, and the front part of my truck's on fire. Why? Well, this cable came in contact with my starter. The starter had run electricity through this gap, okay, and was running a bunch of electricity, huge amount of amperage, making this thing red hot. Now, that should have melted my fuse, but my fuse was a penny, so it didn't melt that at all. And so this thing got hotter and hotter and hotter. It was sitting next to my what? My carburetor. That's the place where the gas and the oxygen get together and explode to make your car go. Yes, gas fumes. So my whole front of my car was on fire. Fortunately, it wasn't my first time, and I'm not going to explain that either. So I got myself a fire extinguisher, blew that thing out, and actually, oddly enough, it fused the end of my my cable to the end of my carburetor, and it melted all the extra cable off. Wasn't that nice of it? I did replace the penny, though, that same day. But in any event, why do I want a fuse? Because I don't want random electricity happening somewhere. I don't want my 3-year-old to stick a tongue into the socket of a wall and allow 100, 200 amps to go through the baby. We don't want that. And so we set it so that if you get above 10, something's wrong, shut it down. Don't light my house on fire, shut it down. Okay, so that's what fuses do. I'm going to have to stop this now and continue on the next video, which we will do in just a second. So get the next